DPF, learning dense prediction fields with weak supervision. Nowadays, many visual scene understanding problems are addressed by dense prediction networks. But pixel-wise dense annotations are very expensive or impossible, motivating us to leverage cheap point-level weak supervision. However, existing pointly supervised methods still use the same architecture designed for full supervision. In stark contrast to them, we leverage point-level weak supervision and propose a new paradigm named DPF that makes predictions for point coordinate queries, which is naturally compatible with point-level supervision. In this paper, we showcase the effectiveness of DPF using two substantially different tasks: semantic segmentation and intrinsic image decomposition. Specifically, we introduce a dense prediction field that predicts a value for each continuous 2D point on the imaging plane. Moreover, inspired by the recent success of implicit representations, we use an implicit neural function to implement the DPFs. Mathematically, given a coordinate query x in the image, we predict its corresponding value Vx as this. Due to its continuous nature, DPF is spatially consistent, thus can achieve superior performance under sparse point supervision. The overall network architecture is as follows. DPF is composed of three parts: a dense prediction backbone to extract high-level features and make baseline predictions, a guidance encoder to encode guidance features, and an implicit dense prediction field to make predictions at point coordinate queries. The paradigm can be applied on top of any plug-and-play dense prediction models. In practice, we choose a CNN-based network fast FCN and a VIT-based network DPT as the backbones. For the implicit dense prediction field, to get the dense prediction value for a random coordinate x, we can't directly extract the corresponding value from a discrete dense prediction map. Instead, we get Vx by interpolating the dense prediction values of neighbor pixels. Inspired by deep implicit function methods, we use a deep neural network to get the interpolation weights and dense prediction values as the equation. Given an input image, we can generate dense prediction maps in arbitrary resolutions. Here are the experiment results. We benchmark DPF on three large-scale public datasets: Pascal context, ADE20K, and IIW. We provide both qualitative and quantitative results. As shown in the table, DPF set new state-of-the-art performance on all of them with significant margins. In the quantitative results, DPF also achieves superior performance. We also provide the visualization results on three datasets respectively. The left two figures provide the results of scene parsing. Compared with the baseline prediction, DPF produces more accurate results. Specifically, as shown in the figures, there are a lot of noise patches in the baseline predictions, and these patches are misclassified, making the visualization results look very cluttered. Different from the baseline, there are fewer misclassified patches in the DPF predictions. Besides, the predictions on the edge of objects are smoother for DPF, and the segmentation of objects is also more precise. The right figure presents qualitative results on IIW. As shown in the image, the prediction of DPF is smoother, compared with the baseline prediction. For example, in the purple quilt in the third row of the figure, DPF can distinguish reflections and wrinkles, and decompose the quilt into the same reflectance, while baseline prediction is not as flattened as ours. These results illustrate the capability of DPF on different tasks. Here are some ablation studies, which verify the effectiveness of our architecture. Details can be accessed in the paper. In conclusion, in this paper, we propose a novel methodology for learning dense prediction models from point-level weak supervision, named DPF. DPF takes 2D coordinates as inputs and allows outputs of an arbitrary resolution. We set new state-of-the-art performance on Pascal context and ADE20K datasets for scene parsing, and IIW dataset for intrinsic decomposition with point-level weak supervision. Codes are publicly available. With systematic ablations, visualization and analysis, we delve into the mechanism of DPF and reveal that its superior performance is credited to locally smooth embeddings and high-resolution guidance. Thank you for your watching.